In this pair of example problems, we're actually solving the same system of equations, once using the Jacobi iteration method and once solving it with Gauss-Seidel iteration. Both of the problems would start off exactly the same, would start off by rearranging equation 1 to solve for x1, using equation 2 to solve for x2, using equation 3 to solve for x3. And then we need our initial guess, which will start off at 0, 0, 0 in both methods, and we'll be able to do a direct comparison of Jacobi versus Gauss-Seidel side by side now. So we'll start off by rewriting equation 1 for x1. So we have x1 is equal to 6 minus x2 minus x3, all divided by 3. Then that's x1. And we just solved for x1. The 1 didn't show up for whatever reason. So that's x1. Now we'll have x2, which we write using equation 2. So we have 10 minus x1 minus x3, all divided by 4. Lastly, we use equation 3 to solve for x3, and we have x3 is equal to 7 minus x1 minus x2, all divided by 4. So with those three equations, we're ready to start both these applications. We need to use our initial guess, and we're going to start first with Jacobi iteration. So we're going to solve for x1. After iteration 1, we have 6 minus 0 divided by 3 for an answer of 2.0. Then we have apply equation 2, so we have 10 minus 0 over 4 for 2.50. Lastly, we solve for x3 with 7 minus 0 over 4, or 1.75. So we have our solution vector after iteration 1 of 2, 2.5, and 1.75. Now we use those values to update it and apply the three equations again. So now we have x1 is equal to 6 minus 2.5 minus 1.75 divided by 3 gives us 0.583. Then we take and apply equation 2, so we have 10 minus 2 minus 1.75 divided by 4, and for this one we get 1.5625, 1.56. I'll stop it at 3 just because of the space limitation. Then we apply equation 3, so we have 7 minus 2 minus 2.5 all divided by 4 to get 0.625. We have our second iteration complete. Now we go on to iteration 3. So we take 6 minus 1.563 minus 0.625 all divided by 3 to get 1.271. Then we apply equation 2, 10 minus 0.583 minus 0.625 all divided by 4 to get 2.198. Then we apply equation 3, 7 minus 0.583 minus 1.6, sorry, I'll start over on this one. It's 7 minus 0.583 minus 1.563 all divided by 4, or 1.214. Now we're ready for iteration 4. At iteration 4, we start with equation 1, 6 minus 2.198 minus 1.214, all divided by 3, gives us 0.563. Sorry, 863. Then we apply equation 2. 10 minus 1.271 minus 1.214, all divided by 4, to get an answer of 1.879. Lastly, we apply equation 3, where we get 7 minus 1.271 minus 2.198, all divided by 4, to give us an answer of 0.883. You probably can't see what the exact answer is at this point, but at iteration number 9, we'd finally get to 1.01, 2.01, and 1.01, and that's working its way very slowly towards the exact answer of 1, 2, 1. That didn't work particularly well, but it was working. It was somewhat tedious. But perhaps you noticed that when I was going through that it seemed like I wasn't using the best information. Now watch as we apply Gauss-Seidel. Starts out the same, but very quickly it's different. So when we go with Gauss-Seidel, we start off the same. Apply equation 1. So we have 6 minus 0 over 3 for 2.00. Now we apply equation 2. In the last application we said 10 minus 0 over 4, but this time, instead of going back and using the old information on x2, I'm going to use this updated value. So I get 10 minus 2 minus 0, because I don't have an updated value for x3 yet. So 10 minus 2 minus 0 over 4 gives me 8 over 4 for 2.00. Next, now we have an updated value for x1 and x2, so when I apply x3, I'm going to say 7 minus 2 over 4 for 0.75. Now that, after one iteration, that's my best estimate of the solution vector. Let's try one more application, another iteration. So we have 6 minus 2 minus 0.75, all divided by 3, and I get 1.083. Then I have an updated value for x1, so when I apply the second equation, I have 10 minus 1.083 minus 0.75, all divided by 4, and I get an answer of 2.042. Next, I apply equation 3, where I take 7 minus only the updated value of x1 and 2, so I say 7 minus 1.083 minus 2.042, all divided by 4, to give me an answer of 0.969. Next, I go to iteration 3. 6 minus 2.042 minus 0.969, all divided by 3, gives me an answer of 0.997. Then I apply equation 2. 10 minus 0.997 minus 0.969, all divided by 4, to give me a value of 2.009. Then I apply equation 3. 7 minus 0.997 minus 2.009 gives me an answer of 1.00. I'm now pretty much as many digits as I can copy into this table, getting very close to my answer. So in iteration 4, we have 6 minus 2.009 minus 1.000, all divided by 3. So by iteration 4, I'm at 0.998. And I now apply equation 2, where I say 10 minus 0.998 minus 1.000, all divided by 4, gives me an answer of 2.001. And this answer was going to work out the same, what you'd really find is that even if you used all the digits you could want, you're going to get to an exact answer by iteration 7. So would get 1, 2, 1 by iteration 7. But you could see that we were very quickly, by iteration 3 or 4, we were very close to the exact answer. So the Gauss-Seidel was much faster in this example problem, and it shows you the advantages of Gauss-Seidel. Jacobi can be slightly trickier to actually implement, but almost always we would use Gauss-Seidel.